In the previous chapter, you learned about the concept of a random variable. We used an example of flipping 3 coins in which we generated the following sample space, Triple H, HHT, etc. Remember that a random variable is basically a numerical outcome that's produced from the observations in a sample space. So, for example, if you wanted number of heads, then this would be 3 heads, 2 heads, and so forth. But what made this a discrete random variable was the fact that the numerical outcomes were all countable. In other words, there were no decimals involved. Also note that we were able to create a probability distribution table from the results because of the fact that the numbers were countable. We could just put them in the table and determine what the probability is in terms of how often these actually occurred. We now make the important transition from discrete random variables to continuous random variables. This will imply that the outcomes of our random variable will no longer be countable, and they probably will be including decimal values. For example, suppose we let the random variable x, right here, represent how late your friend is to your party. So this random variable would take outcomes that represent time. So let's just say you're having a conversation with someone and you go, hey, Johnny's 15 minutes late. Well, note that is a countable number, 15, but the reality is you would normally never say, oh, he's 15.2 minutes late or 14.8 minutes late, or 15 minutes, 20 seconds, something like that. You don't say that. Normally you just round to whatever the whole number is going to be. So the reality is, though, the outcomes of this are all decimal values. So we need some way to represent that in terms of a distribution. So a student might ask, why don't we just use the same table that we use for discrete random variables? Okay, so if you recall, we did something like this. For discrete random variables, we made a table. So if we're talking about the number of minutes late, then sure, we could do, 0, we could do, 0.5 minutes late, 1 minute late, 1.5, 2 minutes late, ... all the way up to whatever the higher value they represent is for the distribution. But this isn't going to catch it all. Again, every one of these values is going to be rounded from some value of time. So what about 0.25? What about 0.2 and 0.3? And then you could just keep on going forever. 0.25765, whatever, right? Minutes late. The key is that all of these values of x are on an infinite interval. There's an infinite number of decimal values here, which means they can never be represented by a table. It just doesn't work. It just doesn't make sense. So what's the alternative? Continuous random variables are usually represented by what's called probability density functions. For short, we call them PDFs, just like the file type that we know from using our computers, right? PDF. What are some common PDFs that are out there? Well, one of them is called a uniform distribution, sometimes called rectangular for obvious reasons. Another one looks like this. This is a bell-shaped distribution. Many of you in your heads right now might be thinking, oh, isn't that the bell curve? It sure is. Bell-shaped distributions often are called normal distributions. We will be getting to that very soon, that terminology. But these are all examples of probability density functions. Okay, what about requirements for something to be a probability distribution function? We'll say PDF requirements. Okay, 1, the total area under the curve must be 1. This is a very convenient number. Why? Because when we were doing these tables right here, what was the sum of all the probabilities? It was 1. So it turns out consistence here, in terms of understanding the concepts, we now have a total area. So what do I mean by area? I mean, if I quantified all the area here, then that means the sum inside must be 1. The other requirement is that the height of your curve must be greater than or equal to 0 at all points. Okay, so what does that mean? That means as you move along your curve, you must have a height, meaning these values over here, your y values, that's greater than or equal to 0. So that means it cannot dip below the horizontal x-axis ever. It must be above or on that axis in order for it to be a probability density function. You can see in both scenarios, for this one, we have it on the axis. For this one, we have it above the axis. Okay, so let's expand on our earlier example here. So suppose, let's move all the way down here. Suppose we have this random variable x, which represents how late your friend is to your party. You decide that the latest they could possibly be is 30 minutes. So the span of numbers is going to be anywhere from 0 to 30 minutes late. We're going to let the random variable x be uniform. Okay, so what does that look like? So on a graph, okay, here's our x and y axis. We're going to let this graph be uniform, and the values that you could possibly span for x, which is right here, right, is going to be anywhere from 0 to 30 minutes. Suppose that you know for a fact that this is a probability distribution function. That means that both of these requirements must be met. We can clearly see that the second one is already met because this graph is above or on the axis at all points. Therefore, we need to verify or utilize that. Note that I did change this to a dashed line because I want students to understand that that's actually not part of the graph. The graph is just the straight line that goes across here, whereas this just sort of closes off the graph so that you can see that it creates a rectangle. Suppose that you know for a fact that this is a PDF, a probability density function. That means that both of these must be true. Number 2, very easy to see. If you look at our graph, this line here is always above the x-axis. Therefore, we are good. For the first one, it says the total area under the curve must be 1. So this basically, the area that would be within this rectangle must be 1. You'll note that there's one thing that we don't have right now, and that's the height right here. That would probably be very useful for us. So let's find that really fast, given the fact that the area there must be 1. The area in a rectangle is base times height. So that means we can use that in order to find that height. So let's say we call that h. So we know, first of all, that the area in this rectangle is 1, and we know that the base is 30 long, from 0 to 30. So therefore, if we can actually divide this by 30 on both sides, just some algebra, and that's going to give us 1/30th as the height of this. So this uniform distribution we see here represents the random variable x, which is, remember, how late your friend is to the party. So let's now utilize this graph in order to answer some questions. Assume that the random variable x represents how late your friend will be to the party, which is represented by the above uniform distribution spanning the values 0 to 30 minutes. What is the probability that your friend will be between 15 and 25 minutes late? The first question you might probably ask yourself is, how are we supposed to use this curve right here, this PDF, this uniform distribution, to find probability? What's going on? I mean, it's not like we have a chart like we had before, right? Where we had for discrete random variables, where we actually could find probabilities. Like, what's going on within this distribution here that can help us find probability? Well, if you recall, probability spans the numbers inclusive between 0 and 1. That's one of the main requirements of something to be a probability. Well, what about the area underneath this curve right here? What kind of span of numbers is that going to be? Now note, this can be a little confusing. We're not talking about the span of minutes or the height or anything like that. We're talking about what the area can be underneath that curve. So if I take the whole curve, what is that? Well, we already know that's 1, which means if I want to quantify the area, the max area under that curve is 1. Well, what if I started taking little spans of area underneath this curve? Well, this could be, who knows what it could be, maybe 0.2, let's say. Or if I go to a bigger span of area, that could be 0.5, half the curve, or 0.4, a little less than half the curve, right? So the question is what's the smallest amount of area that could be quantified underneath this curve? Well, if you think about it, the smallest amount of area is none, because it can't be negative. We can't have negative area, which means if we don't accumulate any of the area under the curve, we have 0. So this is where the synergy comes in. If you look at these two things, there is a 1-to-1 correspondence between probability of something occurring and area underneath a PDF. So therefore, if I get a probability of 0.2, that means there's an area of 0.2 between those two values. This is very important to what we're doing right here. Therefore, back to our problem. If you want to find the probability your friend will be between 15 and 20 minutes late, then what do? I'm just going to draw, let me draw a different picture for each of these. So let's go back to this. So this is 30, this is 1/30th, and of course 0 at the origin here. So if I want to be between 15 and 25 minutes late, let's say about halfway is 15 here. So we'll draw a line. Let's do these dash lines. Okay, and 25 minutes late, let's say it'll be about right here. All right, so that means if I want to know the probability that your friend will be between these two values, then all I need to do is find the area between these two values. So remember, 1-to-1 correspondence. So how do I do that? Well, it should be pretty straightforward for you. This is just basic geometric rectangle area. We know that the base of this rectangle is 10, or 25 minus 15, and we know that the height is 1/30th. So therefore, the area, which is base times height, is going to be 10 times 1/30th, which is going to give us 1/10/30th, which is 1/3, by the way, which is approximately 0.3 repeating. So there's a probability of about 0.3 repeating that your friend will be between 15 and 25 minutes late. Why? Because we found the area between those values under the curve. Okay, let's try another one. It says, suppose x equals 0 represents 4 p.m. There is a 60% probability your friend will arrive within the next how many minutes? Okay, this is definitely a unique one for sure. Okay, let's break this down. So apparently right here is 4 p.m. Right, 4 p.m., which means, by the way, that this is 4:30 p.m. because this is 30 minutes late. Okay? It says there is a 60% probability your friend will arrive in the next however minutes. Okay. So what it's basically saying is that if we have a 60% probability, we have an area of 0.6, or if you want to be really specific, 0.6000 occurring underneath the curve. So we're going to quantify that. I would say that's a little bit more than half the curve, and that's going to be 0.6000. They want to know how late they're going to be if this is the case. So if this is 4 p.m., the lateness is going to be this value right here. So in other words, this is our question mark. We'll call this the base of our rectangle. So we're concentrating on this rectangle right here, right? So this is kind of like this calculation that we did before, except when we do area equals base times height, the area is not 1 in our rectangle, it's 0.6. Okay, the base we don't know, the height we do, it's 1/30. So if we want to know what the base is, then we would multiply both sides by 30, and we would end up with 18 as our value. So that means that this person is going to arrive 18 minutes, which is our B now, past 4 p.m. So basically, they're going to arrive in the next 18 minutes at 4:18. Moving on to the next type of probability density function that we encountered, another continuous random variable, we have our bell-shaped curve, which very famously is known as a normal distribution. Turns out that if you are able to identify any distribution as normal, you have a lot of methods at your disposal in order to analyze it. Similar to the binomial distribution, when we were able to use the binomial formula. So what are some important traits of a normal distribution? Well, we know 2 of them already. We know that it has to be on or above the x-axis. It turns out with a normal distribution, it is never on the axis. So these lines right here, this edges of the curves, they go on forever and ever, getting closer and closer to the axis, but they actually never touch it. Also, the second rule for a PDF is that the area underneath this curve is equal to 1. That area, of course, of 1 is perfectly divided symmetrically by the very middle, which we call the population mean mu in a normal distribution. Now note, when we're dealing with a lot of normal distributions in the beginning, we're going to be talking about populations. So that means everybody in the population is going to fit underneath this curve. The middle will always be mu. A side note to that is, if this whole curve has an area of 1 inside of it, that means there's an area of 0.5 on both sides of mu, because it's perfectly symmetric and it folds on top of each other if we were to do that. Lastly, It turns out that over on the curve here, you're going to see that there's going to be a curvature down, which is going to change to a curvature up at a certain point over here. This point is called an inflection point. It, of course, occurs on both sides of the graph. And if you go down from that inflection point, that is going to be where one standard deviation is going to fall each way from the population mean. You, of course, know already that if we were to quantify the observations between these two values, one standard deviation each way, that will equate 68% of the observations by the empirical rule. That is older material and something we have to bring back into the situation. But that will also mean that it'll be an area of 0.68 in between those two numbers. So we'll return to the empirical rule a little bit later. I just want to get sort of the simple concepts out of the way, the introductory stuff, and then we'll get back to that. So what you see right here is you have basically three normal curves. Realize that normal curves can come in all different shapes and sizes. That will depend on the mean and standard deviation. For example, we do have just a number line right here going across. That's all it is, typical number line. We have our first curve, our green curve over on our left over here, that has a mean of -2. So you can see the center here is at -2. And it has a standard deviation of 1, which means the inflection points are probably going to be right here and here to create our first standard deviation marker. If we know this is normal, which we're going to assume here, we would say that this is a normal curve, -2, 1. So the terminology is capital N for normal, and then parentheses, almost like a coordinate. It's not, but almost like a coordinate where you would put your mu and your standard deviation. That creates our first normal curve here. Our second normal curve would be normal 3, 1/2. And our last one would be normal 9, 2. So the means are just changing because we're moving the curves along the axis to a higher value. So there's no really relationship between those values. But there is a relationship here between the standard deviations. For example, if we say that this standard deviation is indeed 1, you'll notice when we move over to this curve and the standard deviation is 1/2, you'll see it's a skinnier curve. Why? Because the standard deviation is now only going to be 0.5, which is going to be about here. So if all of these curves indeed have to have an area of 1, if we shrink the standard deviation, that means the curve has to go up to accommodate the area that needs to be moved around. Same thing goes over here. If we go to a standard deviation of 2, that means it's doubling the amount of our first one over here, which means the only way in order to accommodate the area of 1 is to literally stretch the curve out. So there's a good comparison to this. Have you ever seen a beanbag chair? It is what it is. Like the volume inside of it doesn't change. It's whatever the little pebbles things are in there, right? But as soon as you sit on it, all the area goes out. Well, that's like this. It's like if you literally sat on top of this curve, what would happen? The area would end up going this way and you would fall in. Well, what would you create? You would create more of a curve like this, where then you would be sitting on this guy, right? And the area would end up going, or volume if it was a beanbag, but area if it's a curve, the area would have to go somewhere, it would go into the tails. So all this does is show the relationship between different types of normal curves based on their standard deviation and the fact that they have to have an area underneath it of 1. All right, last thing for this video, let's do an example and see if we can apply some of these things, maybe learn some new things as well. So suppose that the serum total cholesterol for males 20 to 29 years old is approximately normally distributed. Okay, so this is good. We now know it's a bell-shaped curve with mean mu 180 and standard deviation 36.2, based on the data obtained from National blah 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 survey. It says draw a normal curve with the parameters appropriately labeled. Make sure to show where the inflection points would be located. Okay, we can just draw a generic curve for this. Let me make a bigger one over here. Okay, generic curve. You don't have to be super specific by going into like skinny, fat, whatever. We don't have to do that. We just have to draw a generic curve and that'll be fine. Remember that it is normally distributed, so we have the bell shape. We know the mean is mu equals 180, so we're going to throw that dead center right in the middle of this sucker. I'll just put a easy light dash line to show that it's in the middle. We also know that the standard deviation is 36.2. So also, if you want, you can write this is normal 180 comma 36.2, just like we did up here with these guys. So it does want you to, you don't always have to do this, but it does say parameters appropriately labeled. So a good way to do that, especially if they want you to mark the inflection points. So for example, this looks like a little bit around where the inflection changes from an over to an under. So this curves up, this curves down. So right where those are going to be where the standard deviations are. So how do we find those? Well, this guy here, of course, is going to be 180 minus 36.2, and this is going to be 180 plus 36.2. We'll throw those numbers in. This is 216.2. This is 143.8. And I think that would quantify exactly what they're looking for in A. This is a good idea of what our distribution looks like for the cholesterol level of a 20 to 29-year-old male. Now, B. It says an individual with total cholesterol greater than 200 is considered to have high cholesterol. Return to A and shade the region under the curve to the right of X equals 200. All right. So what we're going to do is we're going to go to our curve. We're going to find where 200 is approximately. Well, it looks like 200 is probably going to be like right there, about 200 right there. It's asking us to shade the region to the right of it. So what would that look like? That would look like this. Shading. I usually just use dash lines of some kind, and that will suffice, just throwing it in. While we have completed the requirements for letter A, I don't want to move on, and B, by the way. I don't want to move on until I sort of state the obvious here, hopefully. So remember, the goal of finding the area underneath the curve between or below, above, whatever values was to find the probability. That is going to be the same thing in a normal distribution. That is where we're headed with this. Is, for example, if I wanted to find the probability of a male 20 to 29 having a total cholesterol greater than 200, then that means finding the area in this region. Now, before, that was easy with a uniform distribution, because if we were to block off pieces of area, they were just rectangles. We know the area formula for a rectangle is base times height. We can find that really fast. But my guess is that none of us know how to find the area of this shape right here, which is not a triangle. It's not anything that we've ever probably seen before, right? So that is what the future holds, is we're going to be finding areas in these regions and determining what they are in order to find probabilities. That is where we're going with this. Okay, so our final question here. It says, suppose that the area under the normal curve to the right of X equals 200, so remember this guy over here, is 0.2903. So we don't know how they found this, but they're just telling us it's 0.2903. Okay, so that's what this area, if I fill it all in and I determine what that is, it's 0.2903. They want us to provide two interpretations of this result. Okay, so let's wrap up this video with letter C here. It says, suppose the area under the normal curve to the right of 200, so remember our 200 is right here, is 0.2903. So to be clear here, we don't know how they found this, but they're explicitly telling us that this is the area right in this crazy colored region, right? So there are two ways to interpret that area, which is exactly what this problem is asking us about. It could mean that the proportion of 20 to 29-year-old males with high cholesterol is 0.903. It's a very straightforward interpretation. It could also mean that the probability that a randomly selected male from that population has a high cholesterol, 0.2903. So either one will suffice, but it turns out that in at least this class, you're going to be dealing with a lot of probability interpretations. So that's mostly where we're going to stick. But in your homework or such, if they're asking you for two different interpretations, just make sure that you're aware of both of these.